Welcome back. We now change gears a little bit and start talking of something slightly different. As you can see from the title of the lecture itself, we are now going to talk about atomic force microscope. I do not know how many of you are aware with this name of atomic force microscope, or the AFM as it is commonly known. It is a very unique and a special type of a microscope and is very widely used these days. Okay. Now, you might wonder, in a course of instability and patterning, we have so far primarily focused on the patterning aspect, and we have not talked about in much of instability as of now, but which we will do in the subsequent lectures. You might wonder why all of a sudden we pick up a special type of a microscope. There are many courses available, both online as well as classroom courses, which talk about materials characterization, where you learn a whole lot of techniques, and whenever you talk of seeing something small, you tend to sort of rely on the fact that we go for a microscopy. But if you remember the last couple of slides about soft lithography, we talked that features with 10 nanometer lateral resolution can be made by soft lithography. So, critical question to ask is, how does one see these structures? I mean, you might have made something, but how really does one see this? Because a normal microscope, even the highest end optical microscope with a 100x objective, which magnifies your image by 1000 times, you will not be able to see anything below 400, 500 nanometer or maybe a micron, and that too pretty faintly. The other thing is, we have been routinely talking about topographic patterns like this, and we talked about all sorts of things, height, this, that. Question to ask again is, how do you measure the feature height? Because a normal microscope, what you see, normal microscope, I also include a scanning electron microscope in this regard, where the only difference with an, of course, it is a very advanced equipment, but the major difference with an optical microscope lies in terms of the optical source. In an optical microscope, you essentially use white light to illuminate your sample. In a scanning electron microscope, you use a stream of electrons, so that your wavelengths are small, and therefore you can resolve to a much higher extent. But do not forget, I mean, this course does not permit me to go into the details of microscopy, but do not forget that in an optical microscope or in a scanning electron microscope, ultimately what you see is more like a projection. That is like a picture you take in your camera. It is a 2D projection of a 3D system. So, with your digital camera or cell phone camera, if you take a picture, you are taking a picture of the 3D world, but you are seeing it on a 2D plane. Okay? So, looking at a picture, you really cannot say, suppose two people are standing at slight differences, one is closer to you, one is far away. So, if you take a picture, all you can see is the person who was standing closer to you is appearing larger in the picture, and the person who was standing farther away from you is appearing smaller in the picture. But you can't, looking at the picture, say what was the separation distance between them, how far the second person was standing from the first person. So, what happens is that since you are looking at a 2D projection, the information about the depth sort of is lost. Exactly the same thing happens in optical microscope or scanning electron microscope. You cannot get a clear idea about the feature height, which is very, very important when you are talking about nano and mesoscale patterns. Okay. So, this atomic force microscope, which which is a special and I would say the most popular instrument in the class of a set of instruments, which again is relatively new, early 80s the development started, what is known now as the scanning probe microscope group of techniques. So, this goes by the name SPM, why the name comes, how it works, we will eventually discuss everything in a very simplistic fashion. So, you do not have to be a real big time physicist to understand this. We will have all the understanding, considering that you are an engineering student of an undergraduate college or a postgraduate student in with a predominantly a background in chemical engineering. So, do not worry about that. So, SPM it is known as the scanning probe microscope. Typically, it has two major microscopes. One is the STM, which is known as the scanning tunneling microscope. What is tunneling effect? I will discuss very shortly, but you can just do a quick Wikipedia search what is tunneling, and the atomic force microscope. Why I talked about STM is STM was actually the predecessor of an AFM, and based on the developments of STM only the AFM came up, but STM works only for a conducting surface. So, since we are talking mostly about a polymer surface, STM does not work. An AFM works perfectly well over there. So, we will talk about an AFM in much greater detail, but just to give you an introduction so that you do not feel like left out. I did not I do not know STM, but I talk about AFM. We do not realize that they fall into the same group of methods. I just spend a few minutes talking to you about STM. So, remember that AFM is a special class of scanning probe microscope, probably the most popular class of these methods, and let us see how an AFM works. So, what we are going to do, we are going to talk about the critical components and some operational aspect, as well as we talk about the basic physics, which is extremely fascinating. And we talk about here what is this atomic force, what force exactly are we talking about, and it is actually a nice bridge between the two parts of the course, that is the patterning part and the instability part, because the forces we introduce here or talk about here are significantly responsible for the instability. In the first or the second lecture of the course, we talked about instability, spontaneous instability. So, those instability, as we will see, are caused by the same forces which are used to generate an image in an atomic force microscope. You can guess it. Primarily, we will be talking about the van der Waals force. And we will see how this is used for imaging, as well as in subsequent lectures, maybe after 5-6 lectures, you will start realizing how these forces are responsible for spontaneous instability or different types of instability in thin films. Okay. So, in early 80s, scanning probe microscopes were first introduced, and they were able to produce first real space images of a surface. What is real space image? It is essentially the 3-dimensional images of a surface, so that you do not only see the lateral structures, you do not see only the lateral dimension or only could measure the lateral dimension of the structures, but you also get a true information about the height or the feature height. So, in a normal microscope, so if you have a, let us say, feature like this, in a normal microscope you will see something like this. Okay. In an AFM you will not only see like this, but you will also get an idea about height. Okay. So, this is in a very nutshell, this is one of the major advantages what an atomic force microscope or an SPM group of method gives. So, now SPMs are used in a wide variety of disciplines, including fundamental surface science, routine surface roughness analysis, spectacular 3-dimensional imaging from atoms to micron sized protrusions of surface, living cells also. The scanning probe microscope is an imaging tool with a vast dynamic range spanning the realm of optical and electronic microscopes. It is also a profiler with unprecedented 3D resolution. In some cases, scanning probe microscopes can measure physical properties such as surface conductivity, static charge distribution, localized friction, magnetic field, etc., which is another unique thing. I will don't be really puzzled with all whatever is written here. We will understand all these things. So AFM was discovered, as I already pointed out, it was early 80s. So AFM was discovered in 1986 by Gerd Binning and co-workers at IBM Corporation. This particular paper, if you have the access to PRL, Physical Review Letters, this 1986 paper contained the details about AFM. So it's essentially an extension cum derivation of the STM. And Binning and Rohrer were awarded Nobel Prize. The discovery was so unique that within 4 years of discovery of STM, they got the Nobel Prize in 1986. Okay. If you are interested about the short history of AFM, here is the link you can sort of look into, and you can get a very nice idea. So this is the scanning probe microscope or SPM group of family of techniques. On one side we have the scanning tunneling microscope. There are so STS, STP, scanning electrothermal microscope, scanning thermal microscope, which gives you an idea about the local temperature, etc. For our purpose, please don't be overburdened with these parts. So here we will just talk in a little bit about the scanning tunneling microscope, because this side, the left side of this view graph, whatever you have, don't forget they require a conducting surface. So we will since we are talking primarily about polymer, so we will not worry about them. Next comes the SFM, again a generic name, scanning force microscope, of which of course the most significant member, the major platform, is the atomic force microscope. It has several additional features: lateral force microscopy, phase contrast microscopy, magnetic force microscope, electrostatic force microscope, and also an AFM platform can be used itself as one of the direct write patterning techniques, which goes by the name DPN or deep pen nanolithography. We have talked about some of the direct write methods in while talking about patterning. So here is another method, and I will talk about it in somewhat details. There can be, so an AFM platform can also be augmented with an optical microscope platform, and you can have something like scanning near field optical microscope, which is known as the SNOM or NSOM, which actually produces an optical image, and since you are imaging at the near field, so this sort of overcomes the diffraction limitation. But we will not go into the details of that. We will talk only a little bit about the STM, very little, very fundamental basics of STM we will talk about, and then we will move on to an AFM. So I will, as I have already pointed out, I will try to give you a sort of a perspective so that you understand the operational aspects of an AFM along with the physics and the key components. Now AFM sort of started to hit the market, or commercially they started to get available in early 90s, and now very many companies in the world make their own atomic force microscopes. Various institutes in India now have AFMs, all the major IITs and many other research institutes. So AFM is pretty routine now, but still the physics is extremely fascinating, and if you understand how the images are generated, I am sure you will really like it. And also it is important from the standpoint of using an AFM that you understand the basic physics, because that will really help you to enhance the resolution or quality of your image to a large extent. Okay, so this is how we will proceed. So this is what is a scanning tunneling microscope is all about. It uses a very sharp metallic tip to scan a metallic surface or a conducting surface. Now this is based on the concept of quantum tunneling, which very simply put, when a conducting surface is brought, or a conducting sharp tip is so you have a sharp metallic tip, let us say very sharp metallic tip is brought in contact proximity, in very close proximity to another metallic surface, and you apply a voltage or a bias between the two. what happens is that though there might not be direct contact between the two, you still can have a flow of electrons between these two surfaces like this. So, this is what is known as the tunneling current, and the tunneling current, once you start having, so once you apply a specific voltage and you have a tunneling current, the magnitude of this current is a function of the separation distance between the tip and the sample, or between the tip and the surface. So, in other words, if you decide to move your tip along with the voltage over the surface at a constant height, and the surface is something like this. So, as the tip moves, there is now a variation in the separation distance between the tip and the surface. So, as a consequence of this variation in the height, so let us say it is d1 over here and d2 over here, what is going to happen as the tip moves? So, the location 1, the tunneling current, the magnitude of the tunneling current will be different from the magnitude of the tunneling current at the second location. So, this is the principle based on which an STM works. So, idea is that you take a surface. So, this is we are seeing from the top, you have the tip like this, and the tip sort of rasters. So, what is raster scan? It is more like a do loop. So, the tip starts from the one edge, goes all the way up to here, comes back, it starts from here, goes all the way up to here, comes back, goes to the next line, again goes, comes back, again goes, comes back, like this. So, what are the essential features? You have a sharp metallic tip, you have a conducting surface, you apply a bias or a voltage, and then the tip scans or rasters. Now, since the magnitude of the tunneling current is a function of the separation distance, so the undulations of on the surface, during the undulations on the surface the tip encounters during undergoing this raster scan gets reflected in a change, gets reflected as change in the magnitude of tunneling current, and then you can map this. There are two different modes. I am going to talk about it very quickly and very shortly. But this can itself, the variation in the tunneling current itself can sort of act as a measure of the surface topography. So, here it is, when a conducting tip is brought very near to the surface to be examined, which has to be a conducting surface also, and a bias, which is a voltage difference, is applied between the two, then electrons tunnel through the vacuum or air between them. Of course, this typically works in vacuum, so that the tunneling electrons do not collide with the molecules of air and sort of ionize and get distracted. The resulting tunneling current is a function of the tip position, applied voltage. So, tip position essentially here means the distance between the tip from the surface. Okay. And the applied voltage and the local density of state of the sample. You can ignore this, or if you are interested you can look into what local density of state means, but forget about that. For a specific sample at a given condition, what is more important is that the tip position and the applied voltage, they sort of determine the magnitude of the tunneling current. So, information is acquired by monitoring the current as the tip's position scans across the surface. So, this particular sentence, if you paragraph, if you now look at, we have already talked that the tip sort of undertakes a raster scan, and one can monitor the information is acquired by monitoring the current. How it is done we will see. Practically, STM can be a challenging technique as it requires extremely clean and stable surfaces, sharp tips, excellent vibration control and sophisticated electronics, but let us not talk about that. STM can be designed to scan a sample in two possible modes. Okay. So, this is important. You can have two different modes. One is the constant height mode, and the other one is the constant current mode. The one we briefly described over here is actually the constant height mode. So, you maintain a constant height and go on scanning the surface or raster the surface, and these undulations, as the tip at a fixed height encounters the undulations, you keep track of the change in the magnitude of the tunneling current, and from that you try to reconstruct the surface, understanding the fact that if your tunneling current, if the magnitude of the tunneling current is higher, then the surface was closer to the tip. If it is lower, then the surface was further away from the tip, and so you can reconstruct the surface. So, this is constant height mode. The tip travels in a horizontal plane above the sample, and the tunneling current varies depending on the topography and the local surface electronic properties of the sample. The tunneling current measured at each location on the sample surface constitutes the data set, which is the topographic image. So, essentially the variation in the tunneling current itself is a measure of the topography of the surface. The other mode, in the constant current mode, the STM now uses a feedback loop. Okay. So, in addition to the hardware we have already talked about, so you have a tip, you have a conducting surface, you apply a bias, and you also have a feedback loop. This is important, and you are all chemical engineering students, so you all understand what is a feedback. So, what it does, that you have a set point, specify a set point, in terms of the tunneling current, now the tip starts to raster or starts to scan. So, let us say this was the set point with C1, it goes to the second location where the current is now C2, okay, because of the surface topography. This C1 minus C2 is now the deviation from the set point or the error. This error is now fed to the feedback loop, which then allows the tip to move up or down. Okay. How it is moved, we will discuss when we talk about an atomic force microscope, but this error is now fed to the feedback loop, so that it adjusts the position of the tip. So, let us say the tip was here, it was corresponding to a So, this is let us say the set point configuration, the current was C1, it has now gone to the second point, the distance has increased. So, the current has reduced actually. Okay. So, this C1 minus C2 is now the error, and based on this the error is fed to the feedback loop, so that it allows the tip again to come back, so that this distance matches this distance here, and the current again becomes C1. So, in this case the location of the tip itself reflects the contour of the surface, and you can generate the image like this. Now, it is important to understand the existence of the feedback. We are going to talk about it in greater detail, because all the commercial or the current AFMs work with this feedback loop mechanism. So, this is in a very brief nutshell the operation of an STM. Important thing to need is that the principle of STM requires tunneling current, and which is possible only with a very sharp metallic tip and a metallic, or again a conducting surface. And therefore, though it is extremely useful, scientifically extremely fascinating, it has unfortunately limited application in terms of polymer structures, imaging in polymer structures. However, still I think this much amount of fundamental knowledge in STM will help you both to understand how the AFM evolved, and also STM as a technique itself is extremely powerful, and there are many application areas where the STM finds rather significant application. With that, we now move on to atomic force microscope, which, as I have already pointed out, is to a large extent based on the developments related to STM, or in every true sense the STM was the predecessor of the AFM. So, let us see what are the advantages. Firstly, the first thing, without going into any details, you need to understand that AFM does not suffer from the one major limitation which is there in an STM. AFM does not require a conducting sample or a conducting surface and can work for any type of sample. Therefore, since it does not require a conducting surface, it cannot work on the principle of tunneling, but it works on the principle of something that is more fundamental, and that is the interaction forces between molecules or particles or surfaces. So, AFM relies between the interatomic interaction forces. Now, one of our previous lectures we have actually talked about these interaction forces, and I think I have already introduced you to the concept of van der Waals force. We will revisit it today. So, this is what we can be an atomic force microscope. Do not go into the details of the definitions and all these things. These are things that everything you will understand how it works and all that. In an atomic force microscope, the imaging, or more accurately the information about the topography of a surface, is done based on the modulation of interaction forces between two atoms. So, interaction forces, this is important. We talk about the interaction forces between atoms or molecules. In reality, we cannot go down to the atomic level, and we work based on the interaction forces between two surfaces. Okay. In reality, the instrument operates based on the interaction between two surfaces, the sample and a sharp tip. So, here also you have a sharp tip and you have a sample, but unlike STM, there is no tunneling effect arising out of the tip, but we will see how exactly it differs. So, this is in a nutshell the heart of an AFM, the operating heart. So, here you have a tip. So, here you have molecules, and here you have the surface molecules. Okay. So, the instrument essentially works based on interaction between the tip and the surface. Okay. This is a picture which you will see again and again and again. This is this particular technique, which is now the standard, industry standard of a cantilever mounted tip and a laser and a photodetector. This is known as the beam bounce method. We will understand. So, get used to this figure, but I can assure you that after 2-3 lectures, when we complete atomic force microscope, you will understand every single component of how it works and what it means. Okay. So, with an open mind, let us start understanding an AFM, how it works. So, first thing we need to understand, what is this intermolecular interaction forces we are talking about. Now, these forces are the so called van der Waals forces, and I am sure that you understand to a large extent what they are. They are the most fundamental form of force. Somebody who has a slight confusion. So, this is a nucleus, and then you have the electrons which are in an atom, for example, you have the electrons which are encircling the nucleus. Now, this is a picture I am sure you have got used to from your school days, late school days, maybe 7th or 8th standard. This is a picture we used to draw. But reality is that it is not so simple. The electrons are not like this isolated discrete entities rotating like the planets. I am sure in your school days you also learnt at some point or the other what is the similarity and the difference between the electronic structure and the solar system. In reality, it is a very high frequency oscillation of the electrons around the nucleus, and at any given instance t 0, let us say, what happens is there is a charge localization. The moment there is a charge like a localization, this leads to a delta minus charge which is localized over this area. Now, this delta minus charge, what it does, it sort of induces a delta plus positive charge on the neighboring atom. Okay. And therefore, since this is this has opposite polarity, the nature of interaction is sort of always attractive. But what happens is this delta minus is a temporary localization. So, we are talking about molecules which are charge neutral, and there is no permanent dipole. So, even in a charge neutral non-dipolar molecule, you have this phenomena occurring at all instances of time. So, this is the type of interaction which is known as the induced dipole type of interaction. This is what is known as the Lifshitz van der Waals forces. And this is the most fundamental form of force. Now, what happens is at the subsequent instance, what happens is this localization, the position of this localization now changes. So, this is now let us say localized here, and it induces a charge over here. So, this force or this attraction, though the overall nature of the interaction is attractive, there is no physical attraction present or any bond formation takes place, because of the fact that the charge localization sort of the position of the charge localization changes with every instance of time, and therefore, this attraction sort of is dispersed over the entire material or entire bulk of the material. So, this is also often referred to as the dispersion forces. So, this is available, or this results in all materials, and some of you might be knowing that this is the most fundamental form of any force. What is important to realize that though this is the most fundamental form of force, in reality or in our macroscopic world, we hardly see the signature of van der Waals force, and everything we see is sort of a function or dominated by gravity. The reason for this is that this interaction sort of scales with, so VDW, the van der Waals interaction, scales with 1 by r to the power 6 between two particles, let us say atoms or molecules. So, r is the separation distance between the two. In contrast, your gravitational force scales with mgh, h is the separation distance. So, you can understand immediately that in the macroscopic world, where h or r whatever, so this can be r, they are equivalent here. If r is large, this term will be much larger than van der Waals force, and therefore, in our macroscopic world, we do not see any signature of van der Waals interaction. However, you can now imagine if r is small, what happens? What happens is that since r is in the denominator, therefore, with progressive reduction of r, this term becomes dominating or becomes much larger, and for very small r at the molecular level or at the mesoscale, the van der Waals force sort of dominates at a much higher rate as compared to the gravitational force. Now, one of the things that is interesting to note is that we talk so much about nanotechnology. Okay, so everyone is talking about nanotechnology. Now, there are quite a few factors which make nanotechnology or this particular length scale so unique, and even in the introduction of this particular course we did talk about some of these methods or some of these reasons. But one of the reasons, of course, is the fact that at these length scales, very small length scales corresponding to few molecular diameter, or let us say up to 10 or 100 nanometer, what happens is you also have a very strong signature of these van der Waals forces, and gravity is almost absent. So, many of the spectacular phenomena, so called spectacular phenomena one sees at these length scale is attributed to the fact that the interaction forces or the intermolecular interaction forces have a significant role in some of those phenomena. So, for our understanding, what is important to note that van der Waals force between two particles have a scaling of 1 by r to the power 6, and for the time being you believe me that this sort of stretches, this interaction stretches to roughly around 10 nanometers, definitely not beyond 10 nanometers where this becomes large and eventually. So, for r greater than 10 nanometer V tends to 0. The other thing you need to understand at this moment, and we will take up the derivation in after a couple of classes, is that this same force scales as 1 by r square between two surfaces. How it comes, r square from r to the power minus 6 we will show. So, what happens is the decay, the nature of the decay of the force becomes much weaker now. So, that it tapers off at a much slower pace, and consequently the interaction sort of stretches up to 100 nanometer, beyond r greater than 100 nanometer. So, V W surface, I would say, again tends to 0. Okay. Now, in one of the slides we have already mentioned that an atomic force microscope primarily operates based on the interaction between two surfaces. So, this is more of an important number for us, and we will see how this becomes important. So, the signature of non-retarded van der Waals force, the type of van der Waals force we talked about is an induced dipole type interaction. What has been assumed implicitly is that this induction of the charge is instantaneous. And this is what is known as the non-retarded van der Waals force. But you also have something called a retarded van der Waals force, to which about I suggest that you look into the internet and get an idea of what it is. It is not essentially very important for this particular course to have a very clear idea about it. So, between two fundamental particles the scaling is 1 by r to the power 6 and it stretches roughly up to 10 nanometer. Between two surfaces the scaling changes to 1 by r square and stretches arguably to around 80 to 100 nanometer. The force is in the range of interatomic force is in the range of 10 to the power minus 13 to 10 to the power minus 6 Newton. There can be host of other types of interaction forces between the tip and the sample, like mechanical contact, van der Waals, capillary force, chemical bonding, electrostatic forces, magnetic forces, Casimir forces, solvation forces, etc., some of which we will take up in little bit detail. But the most important thing to realize that an AFM sort of works for mostly based on the van der Waals forces. I'd like to sort of draw your attention at this point towards this particular potential curve. Some of you might be very well conversant with this. This is a typical potential curve. It can be the famous Lennard-Jones potential. It can be any other type of potential. So, what it gives you is an idea of how the force between, let us say, two particles or two surfaces change as a function of separation distance. So, let us say we have two surfaces which are at infinite separation distance. So, then there is no interaction between them. Okay. So, the force is 0. Now, think of the fact that you are progressively bringing in one of the surface in close proximity to other. If we are talking about the van der Waals potential or the force arising because of van der Waals interaction, we already understand that this stretches maximum up to 100 nanometer. The other thing we understand that the nature of this interaction is attractive. Okay. So, here we follow a convention that an attractive force is negative and repulsive force positive. So, this potential curve can be generated for for two atoms or two particles or two surfaces, whatever you want. It is roughly the generic nature will be the same. Only thing is the curvatures and the distances will change. So, if you are talking about, let us say, between two particles, which is easier to understand, infinite separation distance apart, there is no interaction. You bring the particle closer to each other, and then you understand that once you cross this number 10 nanometers. So, let us say it is over here, then the interaction starts, or the interaction is no longer 0, the interaction starts and the interaction is attractive. So, the force is somewhere over here. You also have a scaling of 1 by r to the power 6, and so r progressively reducing, the interaction force sort of increases. So, you get a curve like this till you hit this point where, if you look at the potential curve, you see a sharp increase. So, all the way down to the repulsive regime. So, I hope you have understood this part of the curve. So, this is the point up to which this particular interaction sort of stretches. Now, what is this point? This point is the point where the two atoms or the molecules sort of physically come in contact. So, you have this nucleus, you have this electron, and then they physically come in contact. What is assumed here, or it's easy to understand actually, we assume this the validity of the hard sphere model. But even otherwise, if these two now are in contact and then you still try to force them closer to each other, what is going to happen? There is going to be an overlap of the electron clouds, and there is going to be an electrostatic repulsion. So, that is what is captured here. So, you force them even closer once they have come in direct contact with each other, and you try to bring them even closer. So, there is going to be a strong sharp electrostatic repulsion. So, this is the repulsive regime. Okay. This is the attractive regime, and beyond this point there is no interaction. So, this is we have drawn it for, let us say, two particles. If we now consider this for two surfaces, if we consider it for two surfaces, for example, the nature of the curve will be roughly the same. Only difference is this interaction will now stretch longer, the decay will be slower. We understand that it stretches up to 100 nanometer. So, the decay will be a little sluggish, and the remaining part of the curve remains pretty much the same. So, here it sort of reaches a maxima in terms of the attraction, beyond which a repulsion starts. So, which means that at this point the two surfaces come in direct contact. Okay. And So, this distance, if you can measure, is the minimum separation distance between two surfaces or two molecules that is present, that will be. So, we will discuss this in one of our subsequent lectures when they are in contact. They can't be this is not equal to d0, d0 is not equal to 0, because of the fact that if you try to bring them in absolute contact or make d0 equal to 0, you have to overcome the physical repulsion of the electrons. So, which is not possible, and beyond d0 this van der Waals force is dominated by the electrostatic repulsion, or which is known as the short range electrostatic repulsion forces. So, many times we follow a potential curve like this is the rather famous Lennard-Jones potential. This, I guess, this A by r to the power 6 with a minus sign, now you understand this part of the potential curve represents the attractive interaction due to the van der Waals forces. A is a constant, forget about its number, we do not worry about it. And then you have this B divided by r to the power 12, which is the short range electrostatic repulsion force. Here also you can see that if r is very large, let us say it is beyond 10 nanometer, then both the terms tend to 0. Okay. So, I will probably rewrite it. So, here is the potential curve. This is that, let us say it is the limit 10 nanometer or whatever. So, this is the phi or the potential, this is r, the separation distance, and if you have a potential like this, there can be three situations where r is greater than r 0, both terms tend to 0 and phi tends to 0. So, for a large separation distance, there is no interaction. For an intermediate r, that is in this zone, the second term dominates over the, we assume that order of A and order of B are roughly the same. So, what happens is you have this term, the second term sort of dominates over the first term. So, your phi is sort of a net negative and you have an attraction. For very small r, again since r is at the denominator, so smaller is the value of r, r to the power 12 will start dominating. The first term dominates, and you have phi equal to positive. Okay. Two important points are this point, this is the point of contact, where the separation distance is d0 between two surfaces, let us say, and this point is also important. Here again phi is equal to 0, but there is a difference between the phi equal to 0 over here and phi equal to 0 over here. Here phi is equal to 0 because in this particular area attraction and repulsion both equal to 0. Over here it is different, and the attractive forces and the repulsive forces match each other. So, and beyond this, so this is the repulsive regime, this is the attractive regime. So, beyond this you have a purely repulsive regime. So, this potential curve is going to be very important in understanding the operation of an AFM. That is why I decided to spend some time into it. For the context of AFM, so the way we understood it, it is the interaction between two particles or two surfaces. This also represents for an AFM interaction between the tip and the surface to be scanned, because of the fact that if you now look carefully, this is the configuration of an AFM. So, this is the tip, this is the surface to be scanned. One additional information I am giving you right now, the tip is sharp, radius of curvature varies between 10 to 20 nanometer. Assuming an inorganic molecule has a size roughly of the order of an angstrom. So, we are now talking about roughly hundreds of molecules of the order of that. So, this is also a surface, the tip is not a single molecule at the end like an STM tip, so essentially you are talking about the interaction between two surfaces, and the two surfaces here are the surface of the AFM tip and the surface of the sample you want to scan. So, the interaction between these two at close contact proximity is governed by this potential curve. So, that is why this curve is very important for the atomic force microscope. So, I guess we do a quick recap on this potential curve. We just introduced the concept of induced dipole type interaction, which is known as the van der Waals forces, which is also known as the intermolecular interaction. And we understand that this type of interaction is the most fundamental form and is available or is present even in molecules which do not have any permanent dipole, including in charge neutral molecules. So, we understand that this interaction has its origin in quantum mechanical origin. It is attributed in simple words to the localization of the electron crowd at any given instance of time, which induces a charge of opposite polarity on the neighboring molecule. Since the polarities are opposite, therefore, the interaction is always attractive, but no physical movement of molecules take place because of the attraction, because the localization changes the position at every instance of time and it goes on changing. That is one of the reasons why it is also known as the dispersion forces. Now, this type of induced dipole interaction is known as the Lifshitz van der Waals force or the van der Waals force. There can be other types of interaction as well, which can be the permanent dipole type interaction or the permanent dipole induced dipole type interaction. We are not going into that details. What we agreed that this attraction between two fundamental particles scales as 1 by r to the power 6, and in comparison to gravity, which is mgh, and therefore, at the nanoscale these forces dominate a lot. Between two surfaces, so 1 by r to the power 6, and it sort of stretches up to roughly 10 nanometer. Between two surfaces, the scaling changes to 1 by r square, which we will see how it changes, and therefore, the decay becomes a little sluggish and the interaction sort of stretching up to roughly 100 nanometer. We then tried to understand how these potential curves look like. We also found out that in addition to the van der Waals force, there is a very short range electrostatic repulsion, which originates because of the overlap of the electron charge cloud. And then we introduced the concept of the Lennard-Jones potential, a typical potential, which is also called the 612 potential sometimes. This part of the this particular term representing the attraction, this term representing the repulsion, and we understand that Depending on the value of r, there can be 3 distinct regimes. For very large r, both the terms are 0 and there is no interaction. For intermediate r, the second term might dominate over the first term and you might have an overall, we will have an overall attraction. And for very small r, the first term again dominates over the second term, and we can have an effective repulsion. We also understand that this is the point where the two surfaces of the particles come in contact and their electron clouds sort of start overlapping, and therefore the repulsion starts. We also discussed that this interaction between the two surfaces is going to be very important in understanding the interaction between the tip and the sample in an atomic force microscope. We start discussing the operation and other critical issues about an AFM from this point. Thank you.